I get to say, thanks, Paul, but I don't have a tie.
Gary made me wear it.
I know. Okay. Title of this talk, Motions of the Moon, Why the Moon is Where It Is When We Observe It. Well, if you flip that round as a question, why is the moon where it is when we observe it? You might think this should be the simplest question any amateur astronomer could possibly ask him or herself. Well, it turns out not to be quite the case, as you'll see. I'm going to be giving you a slightly longer talk than usual this evening. It requires it. Now, just for those of you that don't know, I've been giving a series of talks over the last wee while about things in the solar system, in particular to celebrate NASA's very best kept secret, which is that NASA has declared that we're in the middle, by the way, of the year of the solar system. The only problem is they seem to have forgotten to tell anybody about it, because most people aren't aware of this. But if you Google NASA and year of the solar system, you'll actually see their official announcement. So this is one of the talks in that series of talks to celebrate here at the RASC in Ottawa the year of the solar system. Maybe we should tell NASA we're doing it. They might be very pleased. As an amateur astronomer with a geological background, I really enjoy observing the moon through a telescope, especially from my light-polluted urban backyard when I can find the time. Trouble is, the moon isn't always where I expect it to be between these all too rare observing opportunities. Sometimes it's way above my neighbor's roofs, while at other times it's so low in the sky I have to walk upstairs to the top floor and peek out through a window to see where the hell the moon is behind my neighbor's houses. So I decided it was high time that I educated myself in the comings and goings of our nearest and most observable neighbor. Remember, it's the only celestial body whose geography and geology can be revealed by even a modest amateur telescope. So the obvious place to start was the RASC Observer's Handbook. And in fact, I started putting this together about 2 years ago. So I was looking at the 2010 handbook. This is a great resource for amateur astronomy in general, but it has a section on the moon and its orbital behavior. And here's the big but. I found it very difficult to follow because it lacks illustrations and it skips a lot of the essential background information that I needed in order to make sense of that rather dense text. Well, I looked at it again in the 2011 version and in the 2012, and it's just as difficult to follow. By chance, I happened across an article by Jean Meus. He's a Belgian mathematician and specialist in orbital calculation. And I found this article in a back issue of the French magazine Astronomie. Finally, I thought, enough illustrations that I could start to understand the complexities of our nearest neighbor's antics in the sky. And as I say, I began to understand. I'm sure there are still aspects of the lunar orbit around the Earth that escape me, just as I'm sure that there are some among this audience here tonight who understand lunar orbital mechanics far better than I do. But having decided to put together a set of simple illustrations to see how well I could explain the moon's orbital behavior to myself, I thought I'd perhaps turn it into a talk to share with you tonight. Now, I warn you, it's a complicated story. So in order to get the point across, what I'm going to do, I've opted to tell the story stepwise. And I'm going to introduce concepts in an overly simplistic fashion initially. And then I'm going to subsequently layer on the complications that reflect the reality of orbital mechanics. Now, I have to tell you, of all the talks that I've given here at the RASC on this platform, this was the most difficult one that I had to put together. And I still can't be absolutely sure that I haven't made some mistakes. So let's see how well I did. Slide, please, Chris. So first, I've got to talk to you about a problem of scale. Here's the true size and scale of the Earth and the Moon, and the distance separating them. If I were to use true scale in the illustrations I'm going to show you, you wouldn't be able to make out head or tail. So my graphics are truly Mickey Mouse sketches, but I think they get the message across. Chris? So let's start with a very simple Earth-centric geometry as a reference frame. The Earth spins on its axis like a child spinning top, and thereby defines the equatorial plane as shown here with the green horizontal line. Next one, please, Chris. Now let's add the Moon and its orbital plane, so that we now are looking at the Earth-Moon system. Now remember that the Moon rotates on its own axis in the time it takes to orbit the Earth, so we're always looking at the same face of the Moon from an Earth-centric point of view. Now this is nothing special. Most moons do the same thing for reasons I won't get into here. However, for a quite different reason, the Earth-Moon system is remarkable. Of the large moons in our solar system, only the Earth's moon and Neptune's moon, Triton, do not orbit in the equatorial plane of their host planet. Although Sirius's Iapetus shows the same behavior and is larger than your average small moon, it's still not in the same size class as Earth's moon and as Triton. Now, even Uranus, with its axis of rotation lying almost within the ecliptic plane of the solar system, the plane that approximately contains the orbits of all the planets, and hence, therefore, its equatorial plane, that's to say Uranus's equatorial plane, is nearly perpendicular to that ecliptic, it's still surrounded by moons that orbit the planet within the planet's equatorial plane. Triton's weird in any event, because it orbits backwards around Neptune, which is why most astronomers assume that Triton was actually a wandering rogue body that was captured by Neptune sometime in the early part of the solar system's history, which leaves our moon. And remember, our moon, its orbital plane sits at approximately 28 degrees to the Earth's equatorial plane. And our moon formed from the collision of a Mars-sized body with our own home planet. So as I said, this leaves the moon looking pretty well unique in terms of its orbital behavior, at least in its size class and within our solar system. Next one, please, Chris. So if now you add the solar system's ecliptic plane to the Earth-Moon system, we now have a further complication. The Earth's spin axis is itself tilted at about 23 degrees to the ecliptic plane, which then means that the moon, while orbiting close to the ecliptic, makes an angle of approximately 5 degrees to the plane in which the rest of the solar system is trying to orbit and rotate. And I think it's this angular difference between both the ecliptic and the equatorial plane of the Earth. The moon's in sort of a hybrid position. I think it's this that gives rise to many of the complications we're going to actually examine here. Next one, please, Chris. So here I've represented the orbital plane of the moon as a red ellipse, tilted with respect to our point of view. And to keep things simple, the solar system's ecliptic and the Earth's equatorial planes are represented as simple traces or lines. Hit go again, Chris. There we go. I think you can clearly see here that depending on where the moon is on its orbital merry-go-round around the Earth, hit it twice, Chris. It will sometimes be above the ecliptic and or the equatorial planes, and sometimes it'll be below them. Hit it again twice, Chris. There we go. Because the Earth spins on its axis much faster than the moon orbits around the Earth, this height in the sky determination is not a function of the time of day. It's clearly a function of the time of the month. Next one, please. So if we now introduce the sun into the picture, we can start to predict which phases of the moon within a given month will ride high in the sky and which will ride low. In this particular example, looking at the Earth-Moon system from space, the full moon, as seen from Earth's northern hemisphere, that'll be the full moon right there, okay, because the sun's over right there. The full moon, as seen from Earth's northern hemisphere, will ride above the equatorial plane and therefore moderately high in the sky, just about above my neighbor's rooftops. While 2 weeks later, the new moon, over here, will sit below the horizon. Now, in between this phase here, in between the half-illuminated moon as seen from the Earth, is the phase that will ride highest in the sky for northern astronomers, and I will easily see it from my backyard way above my neighbor's houses. Next one, please, Chris. But there's a further complication. The Earth orbits the sun and takes the moon with it. Therefore, approximately 6 months later, when the Earth-Moon system is on the other side of the sun's over here now, the height in the sky of the different phases of the moon observed by northern astronomers is reversed. Let's just flip back, Chris, and flip forward again. You can see how it's reversing depending on where the sun is with respect to the Earth-Moon system. Okay, let's go to the next one. Now, the iconic Atlas of the Moon by Ruckel contains a diagram that shows how the height in the sky of the different phases of the moon varies through a given year. This is important. It's a given year. It's not every year that his diagram will be predictive. And this is a function of the orbit of the Earth-Moon system around the Sun. Now, I've tried to reproduce it here. I'll show you, not this blank. I'll show you what's actually filling in the blank. But PowerPoint drawing tools are pretty limiting. So the straight curves that I'm going to show you here should really be curved curves, but you'll get the point. So hit it. There we go, Chris. So here's what the new moon does. And you can see that the new moon in this particular year, in the winter and at the end of the autumn, is pretty low in the sky. And around about the spring-summer transition, it's pretty high. Next one, please. Whereas the full moon, as you'd expect, is doing the reverse. It's riding pretty low in the sky in the spring-summer transition, and in the winter, it's riding pretty high. Let's go for the next one. This yellow line here is actually tracking out the moon's third quarter. There we go, coming down like this and up. And so you can see that in the spring it's riding low, and in the autumn it's riding high. And if we go one more, and here in the red line we have the first quarter. There's the first quarter. It's doing the reverse. It's high in the spring, and it's low in the summer-autumn transition. So I think you get the point here. Next one, please, Chris. Because the moon's orbit is an ellipse and not a circle, the separation of the moon from the Earth varies over the course of a lunar cycle. In other words, a month. Between closest approach, which is perigee, and the greatest separation, which is called apogee. Next one, please, Chris. So this means that the apparent size of the moon to an Earth-bound observer also varies, as you can see here. And you can see how the perigee looks to you much larger than the apparent view in apogee. Next one, please. So let's now add another variable, or complication if you prefer, to the Earth-Moon system, one that was first derived by Johannes Kepler in the early 17th century. You heard about Johannes Kepler at the beginning of the meeting. Kepler determined that when the moon is close to perigee, in other words, closest to the Earth, its orbital speed is greater than when it's close to apogee, in other words, when it's further away from the Earth. Interesting, but so what? Why should you care? Next one, please. Well, this phenomenon is what lets you see around the corner and glimpse a small part of the other side of the moon, the part you're not supposed to see, as illustrated here. Here's how it works. The constant spin or rotational speed of the moon about its own axis, combined with a faster than average orbital speed when passing perigee, means that the moon has actually orbited beyond 90 degrees in the time it took it to rotate about its own axis through 90 degrees. That marker there is now rotated 90 degrees. This allows us, if you look at this line of sight here from the Earth, this allows us to see a bit more of the moon along its trailing edge. That's the trailing edge on this side here because it's going around like this. As the moon slows its orbital speed, swinging around apogee, the reverse occurs. And we get to see around the leading edge of the moon. So again, here, that line of sight taking us to here. Technically, this phenomenon is known as the libration of longitude, and you can find predictions of what this means for observing, in other words, for you and your telescope, every month in the main astronomy magazines, or you can check it out on the web. Next one, please, Chris. So if we now put perigee, apogee, and libration together, this is how the moon would appear to you, speeded up, of course, if you could stare at it without taking a break for a whole month. Notice it's changing in size, apparently. It's rocking left and right, apparently. It's and the migrating terminator and the shadow pattern sweeping across the surface. So this is why one look at the moon is never enough. It's forever changing in its appearance. Next one, please, Chris. Okay. So now that we've established the fundamental components of the moon's orbital geometry, let's take a look at some of the consequences, because this is the interesting part. Because the moon's orbit is oblique by about 5 degrees to the ecliptic plane, it intersects that ecliptic plane at 2 points, technically referred to as nodes. The line linking the two nodes is called the line of nodes, and by definition it lies in the ecliptic plane. So there are the nodes, and there's the line of nodes linking them. Now, this diagram tells us that for most of the time in any given lunar orbital cycle, the moon is either above or below the line of nodes. So the question from our point of view is this: what happens when the moon coincides with the line of nodes? And the answer is it all depends on the sun. Next one, please, Chris. Now, the sun, by definition, lies in the ecliptic plane. And according to this overly simplified diagram, when the moon lies along the line of nodes, as here, for example, the sun and the earth and the moon are in line, and lucky observers on earth get to see an eclipse. Which kind of an eclipse depends on the location of the moon along the line of nodes. Here we see the moon located at the node between the earth and the sun. Earth, sun, moon. Which results in a solar eclipse as the moon blocks the light of the sun. Next one, please, Chris. And in contrast, when the moon is located at the node on the far side of the earth from the sun, we get to see a lunar eclipse as the moon enters the earth's shadow. Now, this sounds really nice and simple. Why am I standing up here telling you this? Because we have a major problem. These last two diagrams imply that we should be seeing a total solar eclipse every month, followed by a total lunar eclipse 2 weeks later. And this is not what happens. In fact, eclipses were notoriously difficult to predict for pre-scientific societies, as some astrologers found out to the cost of their lives. If we want to understand the role of the moon in eclipses, we need to introduce two more complications to this rather simple story so far. Next one, please, Chris. So here's the first one. So far, we've talked about the long axis of the elliptical orbit of the moon as though it was fixed in orientation with respect to the stars. And it's not. It would be fortunate if it was, but it's not. It rotates. And it rotates, hit it again, Chris. There we go, that's what we're missing. It rotates in the same direction as the moon orbits the Earth, and the Earth spins on its axis and orbits the sun. In other words, in the same direction that most planets and moons orbit and rotate in our solar system. This rotation of the long axis of the lunar orbital plane takes about 9 years to complete. Next one, please. Now here's the second complication. That line of nodes, which is this thing here, there are the two nodes and there's the line joining them. That line of nodes also rotates within the ecliptic plane over a period of approximately 19 years, about twice as long as the rotation of the long axis of the lunar orbital plane. But it rotates in the opposite sense. It's called retrograde rotation. In other words, it rotates backwards. Now, I had to struggle with this concept of backward rotation for quite a while before I finally understood, or at least I think I do. I'll explain in the next slide. But before I do, why is this important? Why do we need to complicate our lives with yet another complication? It's important because the rotation of the line of nodes, that's this thing here, the rotation of the line of nodes within the ecliptic plane really makes a mess of predicting when the line of nodes will point to the sun, and therefore when eclipses can occur. All of which means that predicting when eclipses, lunar or solar, will occur depends on knowing when the moon is located at one node or the other, and when that line of nodes is aligned with the sun. This is not an easy problem to understand, but I'll try and walk you through it as simply as I can. Next one, please, Chris. First, we need to answer the question, how do things rotate both forwards and backwards at the same time? And if we look at a simple orbital ellipse, that's the thing that's marked in the red dotted line here, and its intersection with the ecliptic, which is drawn here as a yellow elliptical thing, then we can define the line of nodes. There we go. The nodes are there, and there's the line of nodes. Next one, please, Chris. If the orbital ellipse now rotates, hit it again, the line of nodes must rotate in the same sense. So we've got a problem. We're missing something here. We know the line of nodes rotates backwards, not forwards. What are we missing? Precession. Essentially, precession is the same wobble you see in a child's spinning top, just before it falls over. Next one, please, Chris. Here's a simple Mickey Mouse representation of a spinning disk. The disk is in red, and its spin axis is in white. Think of this as a spinning top. It's going to wobble. If we now represent three positions, different positions of the wobbling top, spinning top, we're going to hit it 7 times, Chris. It's slow succession. Once, twice, 3 times, and again, and again, and again. And there we go. We see that and hit it one more time. There we go. And we now introduce an ecliptic plane in yellow. Something terrible has happened. The line of nodes has not moved. This is because I can't draw. Hit it one more time, Chris. I can't draw, so I've only represented a back and forth rocking of the top. Hit it again. And one more time. There we go. If I could draw for you true precession of the top, the line of nodes would have rotated, either prograde or retrograde, depending on the sense of the wobble. Now, forget the child's top. Imagine now the elliptical orbital plane of the moon with a stake through it at 90 degrees to the plane of the orbital plane. That line, by the way, going through it is called the normal. The orbital plane slowly precesses such that its normal wobbles clockwise, in other words, resulting in a backwards retrograde rotation of the line of nodes. Hit it one more time. While the long axis of the orbital plane itself rotates anti-clockwise, forwards. Hit it one more time. And these rotations happen at different speeds. To put it bluntly, if you watch a spinning top, it spins one way and it wobbles, but it can wobble in the same sense as the spin, or it can wobble in the opposite direction, opposite sense of the spin. And that is what we're looking at. Okay, one more slide there. There we go. So much for theoretical explanations. What does this really mean tangibly for eclipses? Next one, please, Chris. So here's the Earth-Moon system, what it would look like without rotation or precession of the lunar orbit. The yellow circle approximates the ecliptic, and the red circle approximates the orbit of the moon around the Earth. Neither of these things should be circles, but it's easier to draw them as circles. The solid part of the red circle is the lunar orbit above the ecliptic, and the dashed part is the orbit below the ecliptic. So we're illustrating here the tilt. The solid diameter of the circle is the line of nodes pointing at the sun. So an eclipse could occur in this particular configuration depending on where the moon is on its orbital path. Hit it one more time, Chris. So here we see the Earth-Moon system 3 months later. The line of nodes does not point at the sun. There's the line of nodes. This is because I've not let it rotate. So clearly, no eclipses can occur here, wherever the moon happens to be. Hit it one more time. And here again, 6 months later, it's potentially eclipse time again, because the line of nodes is pointing back at the sun, depending, of course, where the moon is on its orbital track. That's what will determine if you really have an eclipse. Hit it one more time. This is way too simple, and it will lead to the wrong prediction. It still leads to the prediction of 6-monthly eclipses. So let's now introduce retrograde clockwise precession of the lunar orbit. Hit it, Chris. All right, so here we go again. At time t1, we're set up here for a potential eclipse because the line of nodes, this thing here, is oriented, it's aligned with the sun. Now, this, of course, all depends on where the moon is as to whether we actually get an eclipse. Hit it one more time. Remember, the line of nodes will rotate clockwise. In other words, retrograde backwards rotation. Next one, please, Chris. So here we are now at time t2. And at time t2, the alignment of the line of nodes is once again pointing at the sun. And this gives us another potential eclipse opportunity, again depending on where the moon is on its orbital track. However, because of the retrograde clockwise rotation of the line of nodes, it took less than 6 months. Less than 6 months for this alignment to reoccur. Hit it one more time, Chris. So let's reinforce this point by observing the next return of the alignment of the line of nodes with the sun at time t3. This is clearly not coincident with the position of the Earth at time t1. In other words, this is not an annual cycle. It's much more difficult to predict. And of course, we still need to know where the moon is as well in order to predict eclipses. Next one, please, Chris. Okay, so perhaps you thought, like I thought at the beginning of this talk, was that the simplest possible astronomical observation was to look up in the sky, night or day, and spot where the moon is. Well, now you know better. Try as I may, I cannot make this stuff any simpler. It's inherently complicated because we're talking about wheels within wheels. Those wheels are not circular. They don't spin at constant speed. their shapes change orientation, and their axes wobble. And this is just the orbital paths. We're not even talking about the objects that are actually doing the orbiting itself. Now, I don't expect you to have assimilated all that I've talked about here tonight in one shot. And in fact, I bet there are some of you that will go out looking for things to read to get a better handle on all of this. If you do, you are going to come across some unavoidable vocabulary. Just check out the lunar section of the RASC Observer's Handbook, whatever the year. For example, what's the definition of a lunar month? You can't get a simpler question than that. Well, you can. The answer is that depends on your reference frame. Bear with me for 2 more minutes and we'll sort this one out. Let's start with the moon, Luna, that's its official Latin name, sitting there at L1. There's Luna sitting there at L1. And this is the new moon with the moon interposed between the Earth, in green here, and the sun. And that, of course, again, is the representation of the Earth's, the moon's lunar orbit. Seen from above the ecliptic, where you're sitting, the ecliptic is in yellow, the moon orbits the Earth, the moon orbits the Earth, that's the red circle there, in an anti-clockwise direction in the same sense as the Earth, which is in green, is orbiting the sun. Hit it twice, Chris. A month later, and I say a month in inverted commas, at L2, the moon returns to the same position with respect to the stars. Hit it one more time, Chris. But because the Earth has moved with respect to the sun on its own orbit, we on Earth have to wait for the moon to keep orbiting the Earth a little longer before you actually get to see the next moon, new moon, here at L3. So to summarize this diagram, the time required for the moon to return to the same position with respect to the stars is called a sidereal month, from the Latin for star. And it takes 27.3 days to complete. Remember that number? We'll have a pop quiz at the end. The time between the 2 new moons, as seen from the Earth, is called a synodic month. And that's from the Greek for meeting or the convergence of paths. And it takes 29.6 days, 2.3 days longer than the sidereal month, in order to compensate for the orbit of the Earth around the sun. Think of it this way. The sidereal month is a month of absolute rotational positions, while the synodic month is a month of lunar phases relative to us on Earth. Next one, please, Chris. Okay, sidereal, synodic, if I can pronounce them, are commonly used terms when talking about the moon. But the RASC Observer's Handbook also refers, cryptically, each year, to 2 other lunar cycles, which you may have heard of, anomalistic and draconic. But unfortunately, depending on the year, the RASC Handbook either has no explanation of what they are, or the explanation is extremely dense. Or rather, it's not even dense, it's fleeting is the word I'm looking for. So if you've stuck with me this far, and I hope you have, these monthly cycles are now easy to explain. Believe me, this is going to be real easy. Compare with what I just told you. Hit it one more time, Chris. Okay, let's see how we're doing. Yep. Now, the anomalistic month is simply the sidereal month. Remember, that's with respect to the stars. The sidereal month plus a small correction of 0.2 days to allow for the prograde rotation of the long axis of the elliptic orbit of the moon. Hit it one more time. Okay. And one more time. Oh, no, go back one, Chris. That'll do. I must be missing something there. The draconic month is the sidereal month. That's, again, the sidereal month is the month with respect to the stars. Is the sidereal month minus this time an even smaller correction of 0.1 days to allow for that retrograde motion of the line of nodes due to the wobble of the lunar orbit. Next one, please, Chris. Okay, so there you have it. The deceptively simple Earth-Moon system is complicated enough to make my brain hurt. If anyone knows of an easy to read, and I insist, easy to read, well illustrated, I insist, well illustrated, and lucid, please, lucid, explanation of the Earth-Moon system on the web, I would be glad to hear about it. I found several reasonable ones, but none seemed complete. It was bits here and bits there. So enough from me tonight. If you want to run through this stuff at your own pace, I'll be asking our webmaster to post it on the RESC Ottawa website when he can get around to it. After all, remember, we're all volunteers. Meanwhile, I hope you found this a useful summary of the complex behavior of our nearest astronomical neighbor that will help you better understand why the moon is where it is when you're looking up at it. Thanks for listening, and happy year of the solar system. I thought you might.
Yeah. I was thinking about what you said about the wobble, but the Earth also has a wobble that traces a circle somewhere in the North Pacific, I believe. And it's over a very long period of time.
23,000 years.
Correct. Does that have any bearing on it?
No, because the wobbles we're talking about are essentially 9 and, did I say 19 years? It's a very, very different time frame. If you could hang around for, say, 5 to 10,000 years, then yes, if you wanted to compare what you were seeing today with what you'd be seeing in 10,000 years' time, then you'd have to take that into account as well. Yes. Meanwhile, while we're just trying to work out why this month the moon seems to be up there, whereas last year it was behind my neighbors' houses at a certain time of the year in a certain phase, this is the explanation. Paul.
Are you aware that the moon is above the horizon more than 12 hours, whereas the stars are only there 12 hours? Since the moon moves eastward among the stars, approximately its own diameter, if you see the moon rising with a star, let's say under it, by the time they set, the star has already set, but the moon is still up. I think a lot of people aren't aware of that.
I wasn't aware of that. And remember, I put that rider. I know there are people in this room that understand lunar orbital mechanics better than I do. Paul seems to be one of them, and I'm sure there are a few others. I know there's a few PhDs in physics in the room.
With all those complications, how did the ancients manage to predict the eclipses so well?
Well, as you know, they commonly didn't. And in certain cultures, the chief astrologer would literally lose his head. And this was one of the most difficult things in astrology to actually predict.